Thank you, Frank, for your presentation. My name is Thomas Schlichter. I'm a senior engineer at the Mobile Communications Group at Fraunhofer IAS, Erlangen, Germany. In this talk, I want to introduce the specific updates for OAI to implement 5G NR in a satellite communications network. Therefore, I split this talk into two parts. The first part is about the pre-standard NR-NTN developments in OAI, and the second part is about an ESA-funded project about the development of a 5G NR-NTN roadmap. First, I want to introduce you different possibilities of satellite networks. We've got transparent satellites, where this satellite basically just forwards all the signals received on one side to the other side, and processing payloads, where we basically can implement complete GNode Bs in the satellite. In the case of a transparent satellite, we see the clear disadvantage that basically the round trip time is quite high because we have to go up to the satellite and back down to it. On a processing payload, basically we can get rid of half of the delay by just communicating directly with the satellite. Besides these categories, we also categorize satellite networks by their orbit. So we've got, for example, geostationary orbits, which means the satellite is basically stuck to the sky. So it's rotating within 24 hours around the Earth. To achieve this, the distance to Earth is quite high. It's something like 35,000 kilometers, meaning only the travel time of the signal from Earth to satellite and back to Earth is around 250 milliseconds. So if the UE wants to communicate with the GNode B and the GNode B communicates back to the UE, this even sums up to half a second of round trip time. This can, of course, be highly reduced by using lower Earth orbits with distances around 400 to 1,000 kilometers. But there we've got another issue. The satellite is now moving with a very high speed over the ground, something like 7 kilometers per second. Because of this, it's also only visible for a short duration, something like 15 minutes. To integrate all these kind of satellites, LEO satellites, GEO satellites, transparent or processing payload satellites, is part of the 3GPP Release 17 work plan. There are different challenges to integrate these. For example, in these variable time offsets of LEO satellites, this can be solved by, for example, having a better time synchronization. We've got very variable frequency shift because of the LEO satellite moving towards UE and away from it. So we have to have an improved frequency error estimation compensation. We've got a large delay, especially with GEO satellites. So here we need to extend the timing advance values and have to adopt the random access procedures. Because satellites are using usually frequency range 2, there's quite some prominent phase noise. And to compensate this, we also have to use the phase tracking reference symbols, PTRS. On the other hand, satellites are using quite a small bandwidth. So they want to use FR1 waveform, but using some features like, for example, the PTRS from FR2. Documents talking about these challenges and possible solutions are 3GPP documents like the TR38.811 and TR38.821. Here on this slide, we are showing some features that we developed and already pushed or merged to the official OAI develop branch, and other features that we are currently working on or developed and are going to be merged. For example, we already provide the implementation of additional DMRS positions for uplink, and we are going to provide this also for downlink. Also, we added the feature of PTRS for uplink, and we'll also provide this for downlink. We also provided the feature of FDD and arbitrary intermediate frequencies, and others like improved time synchronization and frequency error estimation. These are things that we developed or are developing and are going to also provide this to the community. Besides this, there's quite some standardization effort ongoing for 3GPP Release 17, like I already mentioned, the extended timing advance or adopting the random access procedure. And we, Fraunhofer IAS, are actively contributing. For example, in the co-funded ESA project, ALIX. Yes, now a short view or look into our lab. The biggest and most expensive device here is definitely the Keysight PropSim F64 channel emulator with the aerospace option, allowing to emulate LEO or GEO satellite communication channels. Besides this, we also have the Keysight UXM, different USRPs like the X300 and 300s, and high performance PCs, of course. This is a short look into one part of our lab. Here we see, for example, one setup with a UE and GNOB directly communicating, and here we've got a GNOB and UE communicating via the channel emulator. So finally, on my last slide, I want to introduce the ESA-funded project on the OAI NTN roadmap. It's about development of this roadmap, taking into account the decisions from 3GPP, but also the terrestrial feature roadmap of OAI, and of course the times when we've got demonstration opportunities. We want to talk with companies collecting their interests and activities, especially on development of 5G NR, NTN, LTE, NB-IoT, for example, is because IoT over satellite is also very hot topic, let's say. Yes, there we want to identify different gaps, and as said, we want to develop a common roadmap and try to synchronize and even take the demonstration opportunities into account. For example, early next year, we also want to demonstrate already 5G NR downlink only over a LEO satellite, and even a bidirectional 5G NR communication over GEO satellite. As said, the interviews are currently ongoing with companies. So if you want to participate, please don't hesitate contacting me. Thank you very much.